by the way, on closing ceremony, it will be all same people like before, or no, it's just
HOD sir and
okay. I just ask.
Two people, yes.
Yeah.
They are from department only, sir.
Okay. Because welcoming ceremony was very official. No issue.
Just say thanks.
Yeah. It will be.
It's necessary.
Yeah. Of course. I will start. Okay, good morning everyone. I welcome you on the last day, last lecture and last tutorial that we passed today through. And this lecture, number 7, will be related to, we now move from modeling and measurement to practical mitigation algorithm that I will present. Up to now, we could see that wind turbines create complex Doppler clutter and how we can simulate this clutter and measure this clutter. So in this lecture we will have only one goal. Given such data, how we can suppress the wind turbine component without damaging real targets or without, how to say, ignoring the resolution cell, but we won't suppress only our mitigation technique will be based only on mitigation of this DSC component. So we will focus only on mitigation technique based on software solution that will work, how to say, inside the radar. Idea of this mitigation is based on prediction of dominant spectral component that produce especially blade and blade tip at the end of blade, and we also will design adaptive digital filter that is produced by these blades, and we will by this filter remove this DSC component. So I will introduce you during this session AMPD peak detection algorithm that we use for detection of DSC component in spectrum, and also filtration, so prediction of DSC component in next time instance will be based on UKF filter, so it is unscented Kalman filtration method. During the end of the lecture I will present you some results based on real data measurement, so how our mitigation algorithm suppressed. Okay, so first I will remind you what is DSC and what is flash. Second, I will introduce you principle of the AMPD algorithm. It is peak detection algorithm and how we can use this algorithm based on extraction of DSC component from Doppler spectra. Then I will explain briefly how to use Kalman filtration, principle of Kalman filter, and special unscented Kalman filter that could be used for prediction of evolution of DSC component. Last thing will be designing parametric digital filter for based on this predicted DSC frequencies that will remove this DSC component, and of course we will check all results how it looks after mitigation. So we make small recapitulation. So during class day I introduce you phenomena that is produced by wind turbine. It is flash and DSC component. Flash is very strong short reflection with large Doppler frequency that fulfill the whole spectra, and generally any suppression of this flash will lead also to suppression of the real target. So we will focus mainly only on suppression of DSC component, but not exactly the same DSC frequencies, but of course something around this DSC component, because I think that is clear that this frequency most involving your spectra. And we want the rest of spectra will be same, because there could be detected on the rest of the spectra except this various location of DSC component our detection of our target. So if I will go to next slide, there is a small recapitulation of wind turbine mitigation approaches. So I will first introduce infill or so-called gap radar. It is just next radar that you will place to environment where is wind turbine on, especially wind turbine farms. So it is additional radar in your radar network. Next is antenna diagram shaping. It is sector blanking or adaptive nulling so that beam avoids strong wind turbine reflection. But this lead that you can't see in this exact direction in this resolution cell. Then next method was adaptive limitation of side lobes. When side lobe blanking, side lobe suppression and whitening to reduce clutter sensitivity. It is good for CFAR algorithms because they're for adaptive CFAR algorithms. Next one, very promising, was for 3D radars and HPRF and wavefront strategies. These methods are very effective but often very expensive, and long time development of this method for this specific placement site where is located your radar. So it also requires complex like verification and so on and so on. But they are promising. It is like this one and last one we will focus on signal processing approaches. That is relatively publicly unknown because when I already present you state of the art from the industrial companies, there is always only notes, okay, we can make suppression of wind turbine reflections, but principle is unknown. It is clear know-how of these companies, so nobody tell you how they do it. If it's only based on hardware, software, combination of methods, which kind of method and so on. But probably it will be based on some this antenna diagram shaping, adaptive limitation, and then if it's 3D radar by this method. Or of course it could be based only on filtration, on some just pure software defined methods. So what was our methodology of work for designing for mitigation algorithm? First, you always need start with understanding of phenomena based on data analysis. So we just made this step. Phenomena are clear. I already many times mentioned flash and DSC component, so we are focused on DSC component. Then designing of mitigation algorithm based on adaptive filter design, specification of mitigation conditions, so what is level of suppression, what is suppression of the detection, what is local suppression of the input signal, and so on and so on. Then is designing of support algorithms for estimation of wind turbine signal parameters like Doppler frequencies, amplitudes, and so on for adaptivity. Because if you want to suppress in something in some time instance, you need to have already prediction of this value that you want to suppress. Of course, you are not do it like you do it in real time. So you always need to have a prediction of values that you want to already suppress. So it is like this one. Then we make model implementation. Of course, it will be followed in case of successful verification and validation of model. It could be implemented to real radar system. In our case, it is more like academic work because we don't have designed own radar technique. Verification, the principle of verification is, does it work properly? It is suppress desired components, checking implementation. Of course, first version is developed in MATLAB, but then you will probably convert it to some DSP processor or to some FPGA and so on to some specific hardware. Then is validation. It is question, does it work right way? It is suppress wind turbines without additional artifact, and so on and so on. So this is just reminder what is flash. Flash is phenomena which just make reflectivity through all elements of blades. So you can see that there is always and occurs only time by time. It depends on rotation of PRS antenna, visibility of wind turbine PRS, and also on own wind turbines. So we use only 3 blades wind turbines consider, because it is majority of these wind turbines. We need to consider speed of wind turbines, and there is some typical values of PRS parameter. So rotation of PRS antenna from 3 up to 30 RPM, it is like typically values. In some cases could go to higher rotation speed. Visibility of flash of wind turbine by PRS during the flash could be about like 20 milliseconds per 1 RPS, and I need to tell you that of course rotation speed of wind turbines and antenna is not synchronized, it is always unsynchronized. Okay, it could occur that in some special occasions will be synchronized, but it is not typically, so you don't need to count. If will be synchronized, we already saw it, this output, it will looks like static target, because when PRS antenna illuminate wind turbines, it will be blades always in the same position, so it will looks like static object. Probability of flash visibility by PRS, if you will compute from some typical values, it is about 6%. During this 6%, you can just ignoring this affected range cell, because how you can see it is full of spectra, so it is very high level of reflection, and even if we will remove it, these parts, then it's clear that we also remove information about this target. So next one is dominant spectral component. Dominant spectral component is caused by the blade tips with the highest tangential speed. I think that this is clear, we already presented. So this behavior, because rotation of speed is periodic or quasi-periodic during changes of wind turbine rotation, of course, quasi-periodic process, then we saw it already that we have like 3 sines wave that correspond to this end of the blade is, and it is our DSC component, and we exactly want suppress this one, but not only this one, but something around frequencies around this DSC component, because they have biggest influence. This one is a reflection from our tower, and how you can see later, we first need suppress by MTI filter this tower, because our mitigation algorithm will be based on prediction of this DSC component, so exactly these 3 points, but it is the highest Doppler frequency that is in our reflected signal, but in case that we don't remove 0 Doppler frequency, for algorithm this will be like next frequency or zero Doppler, if you get my point. So it not will be 3 points but 4 points. So, and it will be really strong. So he will focus this mitigation algorithm always to this point, almost always. So we need to remove, and then he will focus only on this 3 exact point that we needed. So there is an example of our DST mitigation system procedure. How you can see on the input we have radar data, IQ data. First we compute the Doppler spectrum and usually after passing the data through an MTI filter to remove static clutter. So on this block you have already spectrum but with removing of MTI static reflection. So next comes the blue box, and I will call it DST extraction. So we will apply the AMPD algorithm in this case to locate the 3 dominant peaks in the spectrum. So if you can imagine these 3 peaks in the spectrum, we just want to find these 3 maximas. If we will found it, then we can suppress. We can even evaluate in the next steps where we'll make prediction of this DST component, where will be in next time instance, design filter, and when this next time instance will come, we just use filtration and so on and so on and so on. It is like repetition process. So when we have located this DST or extracted this DST components, we at the current time step we fed them into prediction block, and it is like extrapolation of DST parameter, and it is based on unscented Kalman filtration method or unscented Kalman filter, which estimates based on present value what the DST parameter how will looks in the next time step. All this predicted DST when we design a Doppler digital filter with some specific function that will be focused on frequencies, on suppression of this predicted DST component. So basically I will extract DST components, predict where will be this DST component in next time step, design filter on the present predicted values, and in next time instance I will use this values for filtration, then conversion, and output will be my spectrum with subset of DST components, so it will be this mitigated wind turbine influence. And this is repeated to forever how you have this, how this reflection of course occur. So after filtration we have conversion, this mitigated signal, conversion of mitigated radar signal from spectral domain to time domain, and it is done. And you can repeat these steps again and again and again, of course. So there is some typical mitigation example parameters of result that I will show you in the next slide. So we consider in like 7 RPM of wind turbine, rotation frequency about 10 RPM, carrier frequency again we are in S-band 3 GHz, rotor diameter 90 meter, gondola angle and initialization angle was chosen like this one for example. So there is result of our mitigation algorithm. If you can see on the left side, it is original input signal before mitigation. So you can see tower reflection, one blade, second blade, third blade, and so on. And after mitigation, after we pass through all mitigation algorithm, we get this one. I will also present you results on real data, but this is just for visualization. So you can see that all the highest frequency is like blue one. It is mean really suppressed with comparison with this one. There was about 0, there is about 40, 50, it is depends 40, 50 dB. Of course, you can make complain, what about these frequencies? Yes, there is still these frequencies. It is from blade element that are moving some lower speed, but we can't suppress all. If I will suppress all, I can't recognize what is target and what I want to suppress, what is reflection. But we consider that target will have a higher amplitude of higher. And if not, it will be in this range cell, of course, lost the information target. But it is still better than just work with this. It is definitely better work with this because it is not 100% mitigated, but still mitigated, the biggest influence of this wind turbine. So this is output of our mitigation algorithm. I already present you this final results, but now we go step by step how it works. It is just example that mitigation algorithm works. So first thing will be DSC extraction. So prerequisition on input data will be sampled IQ data of radar signal. It is our output. And first I will use MTI filtration, so I remove static clutter. If I will by MTI filter remove static clutter, you will see that there is no static reflection if you compare with this picture. And now I can put this suppressed static clutter signal or signal with suppressed static clutter. I can pass through for detection of my DSC components, because you can check what will be result in each cut. Always this value, this value, this value. In this cut will be this value, this value, this value. It is like slice, and always you get this red one because it is the highest, of course, level of amplitude. It is this free maxima that we already saw it during tutorial 3. You can see that sometimes for sure our algorithm also fail. When do you think that algorithm fail or not will be so, not work so well? During flashes. Why? How you can extract 3 points when it's everything like on the almost constant level? He will guess, of course, but flash is very short. So our Kalman filter, even during these flashes, will predict where will be the DSC component and will hold it with this for this during a short period of time. And then when flash just disappear, he will again start working. So during this flash, of course, you can expect more like problems, but with these flashes we can't do it anything. Also, I just want to show you that in this case like this, we have 1, 2nd, 3rd. It is clear and so on. But there is like time instance like there, no, okay, sorry. There you have 1 and there you have 2, 3 because there is almost intersections. So imagine one frequency will be very different and 2 other frequencies of DSC component will be really similar. It sometimes could happen. It is due to this interconnection of these DSC components because it is science wave. And why I'm talking about, if you will have these very similar values, then it's clear that next one will be opposite with opposite sign and very high. Why? Because all DSC component, it is like free voltage power generator, how I already present, and this free waves has difference 120 degree. So sum of all DSC component must be 0. So if I have two some very close, next one must be opposite sign and very high to just pass through the condition that result must be 0. Why I talking about it? Because when you will see AMPD algorithm that extract these 3 points, sometimes will show, how to say, little strange values, just like completely outside of range of DSC components, intersections. It is clear because still he need fulfill this to this condition. So before we start suppression, we need to make identification of these 3 components, and this identification is based on automatic multiscale based peak detection, and for this reason I call it AMPD. And this AMPD authors is, I will show on the next slide, we are not authors of this algorithm. This algorithm was presented, publicly available, presented in 2012, and the goal of this algorithm is detection of highest peaks in spectrum or position estimation and so on. Generally, this algorithm works for any type of signal. It is just algorithm, and it is used for extraction of highest peaks in any function. So it not could be only spectrum, of course, but any kind of signal, how you will see. So in principle working like that, find points that behave like local maxima consistently across many window sizes. So imagine that you have window and try found maxima in this window. So you will try, and what will be results? Okay, some maxima, but what on which parameter depends of how many maxima I will found it? On size of window. Because of course, if you will take small size of window, you will detect something is large, you will like make averaging, and you will detect another number of windows. So it is dependent on the size of this parameter, and we need to find, like, how to say, best value where it's fit to our cases. This algorithm works very well only for periodic or quasi-periodic signals, but it is perfectly fit to our case because this DSC component is free sine wave. Or so it is clear. If in case that your signal will be without any noise, you don't need this algorithm. Why? Because you always detect these 3 maximas without any problem. But it will be noisy, then you will have jittering of your signal. And then this jittering, it is hard to make decision. Where is maxima in this jittering? And for this reason we use this algorithm. When struggle this algorithm, when these signals not be periodic, quasi-periodic, or it will have irregular spacing or widely varying peak width. But it is not our case, so because it is free sine waves, when it's changing amplitude or when it's changing DSC components very quickly during only changes of rotation of wind turbines. But this is not so quick process. So for our case, this algorithm was a really good one. Original authors of this algorithm is Mr. Scholkman, Felix, Jen Boss, and Martin Wolf. How I already say, there you have link to original paper with this algorithm. The paper was an efficient algorithm for automatic peak detection in noisy, periodic, and quasi-periodic signals. So you can read the original paper. Principle of this algorithm that we use for DSC extraction is construct is the local maxima scalogram. I will call it LMS. It is a 2D binary matrix where each row corresponds to some a certain neighborhood size. They call it scale, and each column to a sample index. And it is binary. So where will be 1, it is indicate that the point looks like local maxima. And where is 0, it is not looks like local maxima on this scale. So, and after this we will make summation across row, and this gives us a vector whose largest values correspond to robust peak. So exactly where you have this jittering and to some maxima, it will locate this maxima even with this jittering. It will be highly dependent on noise. If your amount of noise increasing, then it's clear that this you can hardly recognize this quasi-periodic or periodic behavior and then fail. MPD provides peak position without necessity tune many different threshold or setting any threshold and so on, because it is like automatic peak detection, because he make variation, he setting this threshold like myself. It is like works like this. So how there I will provide you few more details about this algorithm. So input data to this algorithm, how you can see on the picture, is spectrum computed from IQ samples from measured signal. So it is an individual spectra. So I compute in slow time individual spectra and just feed them to this algorithm. So it is one by one. It is example like individual cuts in Doppler, and you just feed them, and you want to locate these 3 maxima. So as to say, entry in this metric is set according to whether the sample at position E is greater than neighbors. So it is like comparison value. It is greater than neighbors. Then and on what depend this parameter of this thing? It is depends on size of window. So there is variable size of windows, and he always gets some result, and this result is then like sort by size, and this which bigger size, it is big fidelity, that will be this maximum peaks. The conceptual point of work is that embedding peak detection into the multiscale matrix, and it will really become robust against both noise and slow trends in baseline. And imagine, this is relatively slow trend. So and what is noise? It is another spectral lines in spectrum. So it is relatively slow. So exactly AMPD algorithm fit to this our case. So first I will compute computation of LMSC, this scalogram. It will be this matrix, and where results could be only 0 or p, it is some random variable from interval, it is depends of size. So, and key is index of vector of our discrete frequencies. So then I will make summation of all scalograms, and I will make sum of our neighborhood sizes, and we sum each row or equivalently sum of the whole matrix along the scale dimensions, and this will result to some vector where each component indicates how often sample I was considered as a local maximum across the whole scales. And of course, which the biggest values that will be considered as a maximum with highest number, it is my real maximus. There is like a very visualization of this AMPD algorithm. Check. This is this jittering, and you need to find what is maxima. And imagine that one maxima is detected here, 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 here. But from point of view, if you don't use this algorithm and don't see these points, for you it will be hard. It is here, it is here, it is here, because it is very, very varying. So this is like example output, like school example. If I can say of the algorithm, you can see it is just generated in signal in some time, and I add a noise and try use it this algorithm. So I don't use it on spectra, but on some generation of time signal. It is just for presentation of principle. Okay, and then next step, after sum of scalon by rows, we need make rescaling of scalogram. The resulting vector that is there from previous step, we determine global parameters of AMPD algorithm. Especially we are looking for global minimum of transformed version of the summed vector, because this minimum corresponds to the neighborhood size where the overall local maximum structure is best captured. So it is mean that index of this global minimum gives you an optimal scale. And we use this optimal scale that was pre-computed in previous step to reduce the matrix of element and for robust peak detection. This step is very important from point of view makes AMPD algorithm adaptive to the data. We don't choosing some fixed window size for all scenarios. The algorithm infers an appropriate scale directly from the spectrum itself. So we don't tweak this parameter, we just, how to say, algorithm choose this optimization parameter itself from pre-computed from spectra. So then we, in this final step, there is peak detection step. After reducing of the matrix using optimal scale, we compute standard deviation, row-wise or column-wise, it depends, and of course we are looking for result that has the lowest standard deviation, because lowest standard deviation means the lowest error. I am closer and closer to this maxima. So how we already test and make verification of this algorithm? We just generate some signal. It is the upper one. We, of course, we know where is this local maxima. It is the orange circles, and the goal was testing how will this AMPD algorithm detect this maxima under condition of different amount of noise that we adding to our signal. So there you can see that if we use this detection algorithm to signal without noise, then all maxima is perfectly detected. But you don't need to use this algorithm because it will be easy for detection of this local maxima anyway. But if you will use some level of noise, this is example I think that we generate signal from -4 to 4 volts, and level of noise was like 0.2 volts, and like random signal. And then we just make comparison of the green points and orange points, and we could evaluate for different level of noise how this AMPD algorithm is accurate. And there you have like presentation of accuracy of this AMPD algorithm. The orange one, it is original local maxima, and green one is example of like estimated maxima, local maxima of our AMPD algorithm. So you can see, and this is evaluation of error. So you can see that pretty finely this algorithm works for detection of maxima. And after evaluation that we select good, good algorithm for detection of maxima, we use this algorithm for our spectrogram. There is example of wind turbine spectrogram before AMPD algorithm, so it is classic generated spectrogram. And imagine that in each slice now we use AMPD algorithm, and you can see that in each instance you see 3 points always. This, then this, and this. Maybe it is too small for you, but in each cut there is always 3 points. So it is mean 3 frequencies that we need to detect. Of course, it is on simulated data, on real data. Sometimes this extraction failed. It is depends how strong are reflection, how are visible these DSC components, and so on and so on. But works pretty well, how you can see. Exactly follow our free sine wave. Problematic place are where is interconnected in a real measurement, and yeah, where is interconnected. So is it clear? Can I continue? It is just this DSC extraction. So after we know which DSC component are in our frequency spectra, we can move to prediction of DSC. So after this extraction, we for us is interesting how this DSC evolve in time and how we can predict them. So it is mean if you get these 3 values, my next question will be, what will be these 3 values in the next time instance, and the next time instance, and next time instance, and so on and so on. And for this we use Kalman filtration. So you already know, and from presented picture, that Doppler spectrum of wind turbine is really highly complex and depends on many parameters, and from the side of wind turbines and from the side of PRS also. So it is very high dependency. It is depends also on mutual geometry of PRS and wind turbine and so on. So some of these parameters we can measure, or we know them, of course, if we know wind of blade, position of wind turbine, position of PRS, PRI, length of pulse, and so on. So a lot of parameters we know or can be measured, but a lot of parameters is unknown, but they are slowly varying, and it is exactly our DSC component. So we can say also that this slow varying parameters of DSC component, this behavior is slow, okay, but it is for sure non-linear, highly non-linear. Just remember this is non-linear. We use Kalman filtration. Kalman filter, I will talk to you a few words about history. First time Kalman filter is sequential linear minimum mean square error estimator, and it is developed by Rudolf Kalman about in 1950, and Rudolf Kalman published this result of this filtration or estimator in about 1960. From this period of time became one of the most widely used tools for tracking and state estimation in area like radar, robotics, control system, navigation. Almost everywhere is Kalman filtration. Of course, he introduced first version. It was linear Kalman filter and works only on state model that was linear. But you know reality, so nothing is, how to say, not all things are linear. Some things are slightly non-linear, highly non-linear, and so on. So from 1960 until now, it is they still discovering new and new variation of Kalman filter for different type of process. In the red rectangle, you can see original paper published by Professor Kalman in 1960. You can find it, this paper on IEEE if you are interested how looks original contribution. And Mr. Kalman, some history lived from 1930 to 2016. I was curious about that he lived late in USA, and he was founder of one university where was director until his death. So this next two slides will show you on. I will try show you on which principle works Kalman filter. I don't know. Do you have experience with Kalman filtration? Do you have some courses in Kalman filtration theory? Little? Yes? 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 No? Okay. Somebody yes. Somebody no. So. The conceptual operation of Kalman filter is like that. We have prediction step, and
convolution also will use like in convolution network CN.
right. I think that Kalman filter is used almost in any area of signal processing. Honestly, I just mentioned few of them, but I think that you can find it almost anywhere you are. Exactly. And it is same. DSC component is future extraction, exactly. So it is similarity. Right. So in the prediction step, we use a motion model. We call it state transition model to propagate the previous state estimate forward in the time. So this gives us predicted state and associated prediction covariance. So it is how you are sure that prediction values is accurate, like generally say. Then we have measurement step. So we obtain new measurement of some parameter from the sensor. There it will be DSC frequencies extracted by EMPD algorithm. And together with measurement covariance, and again, how I believe in measurement. Because it is affected by noise and extraction error and so on. So I have two things. First, I will do it prediction step, and I have some covariance metrics that told me how you are sure that this prediction is accurate. In next step, I will get result of measurement, and from measure again, and this measurement is also not 100% accurate, but I have some how to say measurement error. And now Kalman filter will make decision. Do I believe more in prediction or do I believe on measurement? And it is based on this covariance matrix. And if I believe more in measurement, okay, and then from this all values is computed by Kalman gain. And this Kalman gain reflected if I will believe more measurement or if I believe more in prediction. Because it could change in time by time, of course, if its measured values accurate more than prediction and so on. It is depends on many variables, and he will always decide if you more believe in one or believe in two, and compute next prediction state. He will make so-called update step when Kalman filter combines predicted state, measured, and using Kalman gain, and then this yield to new state estimation to minimize mean square error under Gaussian assumption. It is important, Gaussian, because if it will be nonlinear, then there is not necessary fulfill condition that will be Gaussian distribution. And it is exactly our case. It is highly nonlinear, so we can use this classic Kalman filtration of like linear Kalman filter, if I can call it, but we use some other type of Kalman filter. So generally we can say that Kalman filter combines two-piece information for final estimation with the small possible error. There is another example how we can look at in, it is used very much often for tracking, so it is just example from tracking algorithm. From the previous estimation, it is this blue rectangular and motion model. Of course, we know what is motion model of target, because the motion model, like example of our plane, can be random, because it is just a limitation of own plane and so on. We can predict where the object should be. So the prediction, we call it, or I call it, maybe you call it by different word, it's extrapolation. And this extrapolation of the next step, it is some extrapolation ambiguity. Then we can get measurement and again some measurement ambiguity. And from all two things, we make new estimation where is position, where is, I don't want to say true position, because of course it is not always true that you will hit exact position, but it is estimation of new position based on these two things, and then start repeating again. And what is your result in tracking algorithm? Just kinematics of your target. And if you will transform this to DSC component, it is same. I will get some measurement, I will predict, I will compare, I will get correction, and again and again and again. Only we just do it for DSC, not for tracking. There is another example from point of view probability density. We have estimation of target. Okay, it is 1D example. So our target just moving around axis X for just simplification. So we know estimated position and speed in this time. I call it times minus 1. In prediction state, first we will predict, we extrapolated this value, and we get something like this Gaussian distribution of our extrapolated value. Then I will receive measurement, and it will be this one. And of course, if will be wilder, then there is bigger uncertainty, so it is mean that this is like worst value than this orange. So our Kalman filter will, how to say, believe more in this one, and from this green one and orange he will make this blue one. It is this correction. And now it is depends if you believe more in green or orange, but you can easily recognize from the shape of Gaussian distribution. It will be more and more narrow. Is it clear that it is more precise and you can believe more on this, like example, their measurement or an extrapolated value and so on and so on. And you combine together and get corrected estimation what will be. So in our case, state vector will be based on DST amplitude, frequency and phase. And the measurements will be DST extracted from the Doppler spectra. So it is just same principle, only I show you on target tracking because it is easy to imagine how it works. And this correction computation of the blue one distribution, if I can say, it is depends on Kalman gain that is computed from these values. No? Okay, I will finish maybe this theory. It is about like, okay, it is about 1-2 slides. If we can finish, and then we will make tea time. I'm checking that you are watching tea. So, if model of measurement is nonlinear, then we need to use Kalman filter modification, because we can't use this standard Kalman filter introduced by Professor Kalman, because it is just for linearized model. So there is two popular nonlinear Kalman filtration extension. One is extended Kalman filter, which linearize the model around the current estimation. So it is just for, how to say, slightly non-linearized model. So it is almost linearized, so it is just like slight non-linearization. And unscented Kalman filter, which use so-called sigma points to approximation the propagation of means and covariances without explicit linearization. So it is for highly non-linear problem. When you see behavior of our DST component, it is really clear that is highly non-linear problem. So we are using UKF for prediction of this DST component. Last slide, and then we will make break. There is some description of our input and process parameters. So state space model for DSC prediction contains parameter DSC amplitude, Doppler frequency, and phase. We define this process model that describes how this parameter evolve between time steps. So largely smooth changes reflecting slowly varying wind turbines rotation, speed, and orientation. Our measurement model maps the state to observe DSC frequencies and amplitudes extracted by EMPD. So state, we know that is 3 sine waves shifted by 120 degrees and so on. And measurement model is extraction value from EMPD algorithm. Of course, we need to define also covariation matrix. Covariation matrix is, I would describe it like by 3 parts. This one is transmission matrix. This one, middle one, is standard deviation matrix. And this is just transposition of transmission matrix. So, but how will looks in reality? For our values, transmission matrix, state vector, so it is amplitude, frequency, phase of our DSC component, DSC. And if you will compute, you will get this result. So what is output of predicted? This is a prediction of one DSC component, one. Okay, you must say, okay, and where I get other 2? Amplitude is always same, it is only phase shifted. So I can easily compute the rest of 2. Okay, so we will make tea break, 15, 30 minutes, up to you. So what do you think? 15, 20 minutes, something like this. Agree? Yes. Okay. And we are just in half of presentation. So today timing is So, can we?
Yeah.
No. So, hello. After tea break, after refreshment, we will continue with lecture. We are just in the half, so I think that we have enough time to fulfill our time management. We will stop on background model of our Kalman filter, and we go next to Kalman algorithm. This Kalman filter, of course, required some initial condition. What is initial condition? It is condition that you need to put to Kalman filter. It is for us, initial condition will be some starting amplitude, starting rotation frequency, and starting phase. But of course, we don't know this. It is completely random variable for us, so you can use any single value that you want. What's happened? In first steps, of course, you will have the biggest error of your prediction state. Why? Because you just guessing about initial condition. You just put random value. So we use 0. Why make so complicated when we can put 0? But you will see that after like few iteration of Kalman filter, this big error will decreasing slowly to some average error, how to say, not of course to 0, but to average error. So it is like this. Now I will, what is inputs to our UKF algorithm except initial condition? It is initial covariance matrix. Initial covariance matrix is defined by this state and is show dependency on sampling period. So it is this parameter Ts, how you can see. Standard deviation of phase and frequency change, it is sigma 1. This is relevance with rotation speed of wind turbine. So small changes in wind turbine rotation speed, because it is also some jittering, or maybe your how to say, your wind turbine starting from 0 to some nominal RPM. So there will be changes, but this behavior is relatively slow with comparison to your PRF, of course, because it is some millisecond, and starting time of small wind turbines is 1-2 minutes, up to big one up to 10-15 minutes, something like this. So if you make comparison of milliseconds and minutes or something like this, it is big difference, but still this could be. And next thing is standard deviation of amplitude variation. It is hidden under parameter sigma 2. So range of expected Doppler it is sigma 2 in our cases is range of expected Doppler frequencies. So there is dependency on blade length, maximal speed of wind turbine, rotation, and so on and so on and so on. So if I will continue, then is next one is adjustable parameters for selection sigma points and their weights. It is 3 parameters, alpha, kappa, and beta, and this parameter, how to say, is hard to like compute in advance. It is more about tweaking. You are trying find the best combination. There is some possibilities how you could set it, but it is, how to say, little magic, because it is highly dependent on your process that you want to follow, and we want to follow our DSC prediction. So the prediction of this alpha, kappa, and beta the sigma points and their weights, this prediction of this parameter was verified and works well for typical values like antenna rotation from 5 to 12 rpm, it is typical values, wind turbine blade rotation from 6 to 20, even 20 is a very high value, and length of blades from 20 meters to 100 meters. And also it is these parameters was verified also on yaw angles, so it is mean angle between PRS and wind turbine. So these three parameters was predicted or was set based on all these parameters. But how it works? You run it for some setting and watching results. If it's not good, you start tweaking this parameter setting and so on and so on. Of course, there exists some possibility how to set some like tutorial how to evaluate this parameter, but still always you need to tweak manually. But it is only one time. After it is valid for all your some typical values, there is constant for you. And these values are used for computation, so call it sigma points, that how to say, that make from non-Gaussian distribution they with minimal error some Gaussian distribution of your process. It is like this. It is relatively complex theory, and a lot of book is related to this setting of parameters and different Kalman filter. So we use these sigma points and these settings. Then we have noise metric of process, so it is noise metric, and another input is prediction of extracted data amplitude, and all these parameters goes to UKF filter algorithm, and there is like example of this complete algorithms like pseudocode Mars description. And imagine that in every time step is always this algorithm passed from line 1 to line 13, and then again there, and continue and continue and continue. This is the whole mathematical pseudocode of your UKF filter. You can see a lot of computation, but everything is like almost metrics based, so you are just repeating and repeating. So first part is extrapolate estimate. So this compute the predicted state, mean and covariance using the process model. It is the blue one. Then is measurement model, measurement processing. It is this brown or which color. Propagate sigma points through the measurement model to obtain predicted measurement mean and covariance. Then is, we can call it innovation. It is compute the difference between actual measurement that comes from EMPD algorithm and predicted values. Then is Kalman gain computed based on think if you believe more in prediction or measurement. And this Kalman gain is used for computation update of the state mean and covariance with the innovation and gain. So it is like how to say, that you make better estimation of your prediction state on base this. You remember this one. So it was extrapolation, measurement, and we make okay, let's call it correction. And this correction is used for computation new values. We return mean value and covariance, and again we start again and we just rotating in the circle for each time instance value. So, oh, there I have mistake. Okay, now we will follow amplitude DSC prediction. Of course, first I want to say that you know that harmonic waves has three base parameters: amplitude, frequency, and phase. And amplitude is usually voltage, current, something like this. But please, I just need to inform you, not in our case. What will be amplitude? The amplitude will be in hertz. So strange. Why? What is this harmonic? What is this harmonic? What is this harmonic? It is instantaneous frequency, the highest frequency. So, okay, this is harmonic signal, but it is not voltage. What is this value? It is highest Doppler frequency. So, I call it amplitude because we simulated this DSC component. But please, it is in hertz. It is like amplitude, if you understand me. Be careful about it because I know that it's confusing. Call it amplitude in hertz. But you need always make relation with this spectrogram and spectrum. So, each DSC instantaneous frequency is derived by this formula. It is first blade, second blade, third blade, and so on. So, amplitude, FB, okay, frequency I will show later, and phase. It is like frequency of blade, but it is depends on sampling. So, this is frequency of blade, sampling frequency. So, this is like discrete frequency of blade, if you get my point. This is for second blade frequency. So, like example, this could be FD1, FD2, FD3. But you don't know it. If it is this FD1 or this FD1 and this FD2 or this FD1, this FD2, FD3, you don't know it. But it will be important. It not will be so easy because you need to know it. But we don't know it. Sampling period Ts correspond to the number of PRR reflection. You understand? You remember from lecture 2. So, typical value is 10-20 reflection or time per one rotation of PRS. So, time of rotation is 60 divided frequency of rotation. So, by combination of this discrete signals, because it is already discrete, it is sampled, you can see there, and after many different mathematical operation, if I can say, we get final terms how compute amplitudes. There I want to highlight my colleague Karel Jurica that discovered this dependency, and it is really huge contribution of his work. And final amplitude prediction terms, because remember we need compute this one, and this one, but for computation of this predicted value I need know this one, and this one, because you can see amplitude is same. So if I will compute this, I know others, and this frequency of blade is also same, and phase is changes about 120 degree. So he discovered that amplitude could be computed by this, and now you tell, maybe you are like checking, okay, I have three formulas for computation of amplitude. It is strange, but check, this amplitude always depends only on two frequencies, Doppler frequency 1 and 2. and their combination, 1 and 3 and their combination, 2 and 3 and their combination. So how we continue? We use all three formulas, and of course your answer can be okay, but you will get three different values. Right, we get three different values, and we want to make minimalization of error, so we will compute average value from these three values, and this we will use like AB, like this amplitude. Of course there is some error, always will be, but it is all is estimation. There is not any exact analytic formula. And what is important, the sum of all DST frequency must be always 0. So because blade shift is equal, result must be 0. So the initialized predicted value is computed like an average, I already told you. And now how UKF we do it, like DST computation step by step. So check. First we make extraction of DST component. So we know extraction, it is output from AMPD algorithm for this localization of local maxima. So we get FD1, FD2, FD3. We compute amplitudes from the extracted data and make averaging, and the result is one single number, one single amplitude. Be careful in hertz. Then this value comes to UKF filtration. So UKF compute first step frequency and phase we will use 0 because we don't know them, and put the amplitude. So in the very first step we know only amplitude, and I don't know frequency and phase, so I put 0. Biggest error in UKF filtration because I am just guessing, I don't know these parameters. I will make estimation, prediction, measurement, and all the whole algorithm of UKF. And what is output? It is this one. So in the next steps I already know phase, frequency and amplitude. The UKF runs and we compute new initial amplitude, phase and frequency. So from second step it is not anymore these two parameters 0, but it is just like done by UKF computation. But we have only guessing of FD1 because we know amplitude, frequency and phase. But we have 3 sine waves, not only one. But if we know this, then it's clear that amplitude is same, frequency is same, and there is only time shift. So I will just make computation of, this is from Kalman filter, it is this one, and this I can easily compute FDP2, FDP predicted 3, and on the basis of these 3 parameters from step 4 we calculate this one, and now we have last problem with UKF filter. How you know if you put these 3 values predicted, that is correspond to first harmonic wave, or maybe it is computed for second, or maybe for third. You don't know. So what we must do? We must make a permutation. So I will consider this one, this combination, this. I need consider all combination, and combination that gives me smallest error, it is the right one. But it is only 6 combination. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And after we assign the best permutation, and how we can evaluate the smallest error. It is difference between FD1, FD2, FD3, and FD predicted 1, predicted 2, and predicted 3. And the smallest differences is smallest error, and it is for me best combination. And then I will go to number 1 and repeat again and again and again and again and again. So this is everything what I want to explain about UKF, and now I will show you some result. Check this picture. It show you extracted DSC, because when we made simulation we know exact position of extracted DSC because I simulate, so I can easily compute. And this is predicted DSC by UKF. So see, the orange circle is extracted, and blue is predicted by UKF filter. So you can see that there is relatively good coexistence, except I don't know if you see in detail exactly where is interconnection of these two harmonics, because he don't know, they are so close each other that he don't know if correspond to one or second one, because he can just make a relatively easy mismatch. There you can see some details. So it is okay, this one exactly, it is two of them. So you can see that is relatively precise. Of course we still working with simulated data, not real data, but it is good. There you can see what is prediction error. So check this. Do you see this first blue line, first blue value? Why do you think that error is about 400 Dopplers? It is really a huge error, because initial condition of my Kalman filter I set to 0, 0, 0, because I don't know anything what was before. So if you want to see how to say average error, just please remove this first value, because it is just on the first value. And then if you will compute average error, it is this orange line. So you can see our UK filtration average error, like average prediction error is about 21.5 Hertz with sigma 41, so something like this. But it is of course varies. It is just example for our parameter that we set for our simulation. You will always get another values. Now if we know extrapolation of DST parameter, I can in time n+1 I can take this spectrum and make finally DST filtration, then just conversion to the Doppler spectrum to time domain, and this is filtered data. So how looks how to say own mitigation? It is this picture show you mitigation block diagram like general principle. First we use AMPD to extract current DSC, it is this one. Then we use UKF for prediction how this DSC will look in the next time step, and this predicted, based on this predicted value, we design filter and we use filtration on this specific spectrum in the same time instance. And this is repeated, 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 and repeated until you need to make mitigation of this wind turbine. So now I will told you a few words about this, how we design this DSC suppression. I want just to tell you that this designed filter, it is just for proof of concept. It is not real filter that you will use in some specific radar. It is just really for proof of concept. We made filtration just in frequency domain multiplication of both spectra, and we are not working in time domain, right, like with impulse response and so on. So it is just really for proof of concept. So mitigation principle is that for every time step algorithm, we configure a filter for suppression of the estimation DST component in the next radar rotation, where you see this wind turbine in your radar cell, and this you are doing one by one rotation. So first, based on predicted values, so it is mean on predicted values of all this amplitude of these Doppler frequencies, we calculate zero and poles of the complex digital filter. And then we calculate transfer function of filter, and then we apply filter, and output is spectrum that is already without wind turbine influence or with mitigated wind turbine influence. So how we design a mitigation filter? Generally, mitigation filter could be any type that you need. It is up to you. If it's finite impulse response filter, if it's infinite impulse response filter, it is up to you. Finite impulse response filter will have advantage that is always stable because there is no poles, but it will be probably higher order. It will be higher order than infinite impulse response filter. So it is up to you. We just use it. Some of them we use it special or not special. We use it notch filter for suppression of all these frequencies. I don't know what is your experience with designing filter from signal processing. Do you have some little experience? For sure you will have some experience with Z transform, yeah. Laplace transform, Z transform. So you know what is zeros and poles. For sure, I am pretty sure. So the this filter is intended for filtration of range quanta with wind turbines present on this only this specific quanta. The filter is generally defined in the Z plane by the position of the zeros and poles. Of course, you know Z plane, unit circle, and all these things. It is standard signal processing. Zeros mainly correspond to attenuation of the specific frequencies. So, where I will make placement of these zeros of filter? Of course, there is predicted frequency of FDP1, FDP2, and FDP3. And poles mainly are used for the gain of the filter. So, the position of zeros will be calculated from knowledge of the maximum and minimum measurable Doppler frequencies, and there is a transfer function of this filter. Check. There is original spectrum. Or no. Yes, it is, sorry. It is original spectrum. And imagine there is 3 values. So I need now to design, it is predicted values what I accept, this FDP1, FDP2, FDP3. And now I will design transfer function of my filter based that these 3 values I want to mitigate. It is like complex filter. Complex is that is not symmetric around mirroring, so it is not symmetric. It is complex, and this is individual notches of the filter. So it is like 3 notches filter, and in every spectrum, in every time instance, the position of this notch is changing because it's changing also in time my DSC component. There is an example. On the left you can see original time Doppler map with strong periodic DSC component with MTI filter. So first thing what are you doing is that you suppress MTI. So this will be blue. Then you make all this prediction and so on and so on, and then you will make filtration. I just want to show you. Do you see this one? Very start of the spectrogram after suppression. You can see that there is still small red ones. So what is mean? It is not suppressed. Why? Because it is this initial condition, we are on start, so our filtration still didn't working. But from different time and time you can see how it's suppressed. So there is example of two spectra. Original spectrum is blue one, so you can see one blade, second blade, third blade, and this is something between this. There will be also, of course, it is not tower because tower is already suppressed. So 1, 2, 3 maxima. And my characteristic, my spectrum of mitigated signal after filtration, it is this one. So you can see that where we have maximum Doppler, now we have minimum. But the rest that could contain your target reflection generally become same, like same propagation of the spectra, and it is exactly what I want. I know if target will be located exactly in this maximum, I will mitigate for sure because I can't recognize, but on the rest I will see this target, and influence of this reflection is mitigated and result is there. Now I present only, how to say, I present only results that is with constant rotation speed of wind turbine. So we was wonder how our UKF filter works if we are changing rotation speed in real time. So it is mean, imagine that your wind turbine is in zero state, so it is mean they are not moving, and now wind start blowing and rotation start from 0 to some value to 7 RPM. So it is linear increasing of speed of wind turbine rotation, and typical starting time from 0 to some nominal values could vary from 1 minute to 10 minutes. About small it is about 1 minute, middle wind turbines it is about 3 minutes, and the biggest wind turbines like this Vestas 150 with blades about 150 meters, 60, or what is it is about 10 minutes. So we slowly increasing, like linearly increasing wind turbine speed, of course, and then we leave it constant. How will looks reality? It is depends on wind, so there will be some always changing in wind turbine rotation speed, but don't expect that in one time RPM is 5 and in second time is 7. It will be some slow time behavior, it not will be so quick, especially with time correspond to your PRI. So scenario was rotation frequency from 0 to RPM, starting time it is 0, ending time about 600 linear increasing from 0 to 7 minutes, constant rotation from 7 to 10. So it is this behavior. And what was the result of simulation? Check. It is our wind turbine rotation speed. So there it's very, very low speed, so it is almost like static object. You can see just really big red one part, so static object. And now I slowly increasing, so you can see how the harmonic waves increasing amplitudes of this DSC component, and from this part it is constant, because it is until 7 minutes, it is from 7 minutes to 10. And we discovered that our UK filter is, how to say, quicker enough to react for this changing in rotation that, okay, this is after, sorry, this is picture after just suppression of MTI. Okay, I was to speed up, I think that I have result. So first what we are doing, it is original spectrum, we suppress MTI of course, and there we made extraction of through AMPD algorithm. So even AMPD algorithm relatively nicely react for my changes in DSC amplitude. This is extracted and predicted DSC component. Of course, there is in some area it is more errors due to these changes, because of course he needs to react and he not always react by good way, if I can say. This is example of extracted and predicted values. Average error was about 10.35 Hertz extracted, standard deviation about 16, and it is this one. And one of the last slide will be a result of the simulation, when in this cut we design of course filtration. So it is filtration, it is transfer function of our cut. And now if you will compute this filtration in frequency domain, so what is just multiplication of original spectra and this transfer function, you will get this result. So you can see it is little more blurred, but still react very well even for these changes in rotation speed. And I think that is one of the, how to say, worst case, because it is from 0 to some nominal speed. And how looks in reality? It will be some variation about some average value of nomination speed, like from 4 to 7, something like this, depends on wind speed, because like it is, this depends on operational states of individual wind turbines, and it is vary from developer to developer, so it is depends how they programming behavior of wind turbines during different speed of wind. I don't know it, also you don't know it, it will be from datasheet or something like this. So this is this filtration, so it is this original spectrum and your spectrum of your filter. This is this is after filtration when you made it. So if I can make a conclusion of this lecture, wind turbine we decompose into flash and DSC component. We figure out that flash is not possible mitigate, that is better ignore this resolution cell, or you can mitigate but it will be equal to ignoring, because you will ignore the whole spectra. But we aim for software only mitigation algorithm of DSC component, we propose three-stage algorithm that was based on extraction of DSC using EMPD algorithm for localization of this local maxima that correspond to three DSC component. I just want to mention that I forgot that this EMPD algorithm we always try detect like two maximas, and the next one is computed because the sum of all three must be 0. But I already mentioned, but I don't know if it's clear from this EMPD algorithm. Then is estimation of DSC parameters using UKF with physically motivated state model that correspond to real behavior of wind turbines. Then we make mitigation of wind turbines reflection using a Doppler digital filter. Proof of concept, please. It is far away from filtration method in reality in real systems, but it is only about designing of filter. So from simulation and measurement results, it's clear that the DSC suppression is about 40 dB or more. So it is, I think, really nice result without strong distortion of other targets. By the way, distortion of other targets depends on design design of your transfer function, because if you will have very steep notch, that you will have little different suppression. So it is just about position of your zero and poles. It is about designing of your filter. You can play with it. But principle of the method is still same. So it depends on you. If you don't like it, our solution, and you want design another filter, it is just up to you. It is just about designing a filter. So during tutorial we will play with this because I have some application for designing a filter and this thing, so you will saw it. We also not only try constant frequency rotation of wind turbine speed, but we also make it is also robust performance for time varying wind turbine speed. So like example, I already showed the startup scenario, but if works for startup scenario, it is clear that will works even in operational mode during changes of wind turbine, because it is even smaller changes, so there not will be issue. And we think that method is applicable to primary radar system processing just by using of just put our black box to signal processing chain in some processing chain. And I think that was last slide of the lecture. We will have one more lecture, lecture 8, but it is just future vision, conclusion, and so on. But definitely I will do it this one after tutorial 4, because it is just also I want. And please start think about your opinion, how you like course or something like this, because I want to know also some feedback and these things. So thank you for your attention. I think that we are almost on time, so today time management is good. Okay, thank you.
उसमें क्लियरली लिखा था कि विंडोज सी में होगा। आई नो तब भी विंडोज सी में नहीं तो उसमें जी में ढूंढता है।
हाँ तो तुम्हारी फाइल वो दूसरे ड्राइव में सेव
तो ड्राइव में सेव तुम किए थे ना जी में।
नहीं, जी में नहीं, वहाँ वो सी में ही थी फाइल।
फाइल जी में तुम इंस्टॉल किए हो, ब्राउज कर सकते थे।
मैं क्या करूँ जब वहाँ पे सी ड्राइव में इंस्टॉल किया तो वो डी ड्राइव में कैसे जा रही है?
लोकेशन तो ब्राउज करते हो, वो सी कह रहा है, तुमने सी में ट्राई भी नहीं किया।
मेरी जो भी सारी फाइल्स होती है डायरेक्ट सी में स्टोर।
I don't want to touch because don't know.
It not will be safe. I remember. Okay, hello everybody after lunch. I welcome you on the last tutorial. It will be related to lecture 7, so we are working with MTI filtration, we are working with UKF and AMPD algorithm, and at the end we will work also with real data measurement and how our mitigation algorithm works on not only synthetic simulated data but also on real data. It is the last tutorial, and after this tutorial we will make lecture 8 that will be shorter one, and it is about conclusions and future work. So we'll see how much time we will need it to pass through all these things. So first, this tutorial will be exactly follow our mitigation chain. So we put all together to complete practical chain for analysis of wind turbine based on microdoppler in real data. We start from raw spectrogram. We will go firstly through AMPD testing algorithm. First I will show you on some how to say test data, so it is mean it will be just few harmonic signals, some of few harmonic signal, some Gaussian signals and so on, and then we will apply AMPD algorithm to the spectrum. Then we will continue with MTI filtration. MTI filtration, I will show you which parameter is based, which parameter we use for this filtration. Then will be extraction of DSC component, then UKF example, extraction data, UKF simulation and measurement, and then will follow complete analysis of mitigation algorithm on different sites. And again we will follow strictly this free site where we already working, like yesterday when you are working during designing scenarios. So what is automatic multiscale based peak detection? You just heard before 2 hours, so I will be little quicker. Goal is detection of the three highest peak in spectrum, and based on this estimation we will put like input to our UKF filtration that will estimate or extrapolate future values based on which we design a filter and we use it for filtration. So please open tutorial 0401 test AMPD where input variables will be standard deviation, sigma and kk. I will call it width where is local maximum searched. So it is mean if you will have higher and higher higher value of this parameter, it will ignore more and more, how to say, local small maxima caused by jittering. So please open MATLAB. Do you have a tutorial for ready? Good. And now please just start with this type of signal. Later you could play with other type of signals. So the last one, and base kk parameter is 40. So it is something like a length of window where you apply this one, this algorithm. Some computation will be more demanding, so please be patient. So if you can check without noise, we get something like this. It is it is localization of maxima on some periodic signal without any mistakes. Of course there is noise, so there is no issue, just detection of maxima by algorithm. If you check on second one and zoom to some how to say, some maxima, localization of maxima is this green dot, and it is not exactly fit to maxima, but it is hard to even predict where is this maxima, of course, because there is amount of noise. So please try adjusting kk parameters. Now is standard value 40, try adjust it like to 30 and run again. So if you can watch it, there is of course another noise because it is random, but I think that you can easily watch it that also there will be more and more some mistake with the definition of this maxima. Try go lower and lower and lower and lower. Okay, and now it is first example 420, because the like size of window, if I can call it, it is now too low. So even in this period he defined one, there one, there one, but due to noise there he is not sure how I can be. So make identification of two maxima, there some maxima, because why? Because behavior of this noise signal is some big differences between amplitude, so he will define that he decide, okay, there is also maxima, but you can say it is not true. So it is clear that if you get again lower and lower, there will be more and more and more and more these green dots where local maxima is identified, but it is not mean that is wrong, if you get my point, because it is depends on setting. Of course, for our mitigation algorithm based on measured data, we just discover some optimal value. So we are not changing this value during processing. But now we are playing with algorithms, so we can change it. So please try go even for lower values, so we can go like for 5, and on which depends this parameter, on type of signal, what is some best value for you. Again, you need to tweak. Check. There is a lot of local maxima because the window size is relatively low, so he not make like weighting, averaging in a very short time, and then it's clear that he have identification of more of them. Maybe just try just opposite, so we will put like 8, okay, like 80. Okay, it is good example. Check this one for 80. He ignored this because it is so big window that again it is just opposite case. He, due to this algorithm behavior, he decide, okay, there is no maxima, so if you will go up, 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 then will be lower and lower number of maxima. It's just opposite. KK lower, more maximas, KK higher, lower number of maximas, because it is the, like weighting. Please try also go back like to some standard value like 30, 40, and try another type of signals. This is relatively good localization of maxima, everything for this 30. And of course, without noise, it will be again perfect. I didn't show you for other cases without noise because it is no meaning, because there it is just clearly nice curve, so there is no issue about identification of local maxima. So I think that this functionality is clear. Please try open this EMPD demo application. There is some more multiple signals. It is also with Guy. There is little, I just consider if I want to show you this application or not, because there is tricky setting between both parameters that you can visible. There is a predefined multiple signals. So signal 1, it is just combination of harmonic function. Signal 2 is sum of Gaussian functions, so like spectrum like peaks, because it is Gaussian, it looks something like this. And signal 3 is sum of 2 Gaussian peaks like controlled spacing. So if you will set noise parameter standard deviation sigma to null, so it is like without noise again, and result is our signal, it is black curve, and blue triangles, it is like naive local maxima approach, where condition is YE is higher than YE plus minus 1, so it is like very naive approach for identification maxima. And the red one is of course AMTB algorithm. So please run this application. And when you have scenario clean, naive SMTB, that, so you can see that there is no issue. Some of Gaussians, again, naive approach, blue one, and AMMPD, red one, you can see also no problem. I put this example of some of Gaussians due to similarity of shape of DSC component. And the last one is close to twin Gaussians. It is close one. What does mean this one? When blades are close each other for some this spectra, how it's rotating, how it's moving, so you know that we have sometimes they are overlapping. So this is almost overlapping cases, but of course we need to identify both maxima, so it is just like typical examples, but it is without without noise. So okay, okay, effect of sigma. There you need to switch effect of sigma and check now. It is for some setting of noise. I hope that will, yeah, it works. Okay, if I will go with sigma of noise to 0, it is my clear approach and there is nothing. And you still remember this is this naive approach, and it is just comparison of two consequent like samples what is higher, and very, very slowly increase this behavior, and you can see that this naive approach totally failed even for a low number, because you can see how many identification of local maxima is with this naive approach. Of course this can't working because it is just adding noise, so there is jittering, and he consider almost everything that is local maxima. But check AMPD algorithm, maybe now you will start complain, okay, but still there should be only 2 of them and I see lot of red one. Of course much more lower number than with blue one, but still. Why? Because I didn't tweak parameter KK. And it is exactly what I want to just describe. Be careful about this, because we always need to tweak some specific value in our cases. So it is algorithm. He need some tweaking of this. So you can, if you will increasing, there should okay, you can see if I will go up, 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 there will be low number, but even in this one, because they are really too close the sum. If we will go for another like sum, you can see blue one and red one almost perfect. Okay, there is due to some setting still one remaining, but you see that localization of this local maxima is relatively stable. So please, 2-3 minutes, play with this setting, try it. If you have question, I will come and answer you. Just try it, play with different parameters. This is like, if this number will be higher and higher, it will be like more averaging, if I can say, so the smaller local maxima will be more and more ignored. But this is very, very big one, so this should be still stable. But maybe for 80 it is relatively extreme value, even this one disappear. Just check it please, because there is a lot, this is just combination of noise. I recommend you tweak always one parameter, not both, because it is hard to discover what is influence this parameter when you are changing in same time noise and same time this parameter KK. So okay, you can see for 45 we have 3 maximas. Blue one ignore, because it is, of course, it's totally failed. But if I will go to extreme, no, okay, check, he identify like 2 maximas only, even for this, but it is extreme value 80. So, and now we will set like this one, okay, this is, yeah. So if I will include the noise for some or harmonics, you can see blue one bad, but red one, even for more and more noisy, still works pretty fine. And still works, because there is big differences. So you can see that local maxima bar AMPD relatively works nicely. And if I will change KK, what this mean? That I will take bigger, like averaging window, windowing, and then even start ignoring me this local maxima because it is too much big. It is too much big value. So like this one. Okay, it is too much big noise, it is almost 1. There could be visible that even for closed twin Gaussians, algorithm will have sometime problem because they are so close, and second is smaller and hardly visible, that this local maxima for some amount of noise will be hardly visible. So if I will go with noise low, it should be improving, but still there will some remaining. So it was first scenario. Second scenario, it was some of Gaussian. This one, this effect of KKs for second scenario, you can see that naive approach working. Of course, we don't have noise. AMPD peaks for KK, it is the red one, works. For green one, KKL12 works. But for purple one, KK30 didn't work because it is not so big one, and he will ignore him this algorithm AMPD. So it is this one. Another scenario is noise environment. It is effect of noise. So in case that you increase sigma, naive peaks, I just call it explode because I don't know how to describe anyway, it is just stop working. You can't use it for which value you want to use it. Free the strongest from the blue one. MPD still show a small stable set of peaks. I don't say that they are free of them or something, but really small set. But again, depends on KK, so you need to tweak. But of course, for some scenario from wind turbine could work some value, for some another value. Okay, sometimes failed, but for this reason there you have UKF that still won't make it is bad measurement, believe more prediction, and so on and so on. So you have like a little control mechanism of this output. Sometimes happen, it is depends. So, and the last one is scale with noise. It is influence of KK. So small parameter, high resolution, but low robustness. I could show you a lot of results that are not, they are not true. It is just local maxima, but we don't want this local maxima from point of view DSC. So medium KK spacing gets larger, go to more scales, naive peak, it is still mass. AMD peaks, mostly just 3 main peaks, so relatively work. And for large value, even our DSC sometimes can just disappear due to fact that we make big windowing function. So if I can say about AMPD algorithm, small, more sensitive, resolves closely spaced peaks, but also let through noisy peak. So this noise, it is generally depends on noise. If will be noise very high, you will see a lot of peaks that you don't need. Medium, good trade-off between resolution and robustness. So something like this, good value between 20 to 30, something like this, what we are using. And now it is important, it is also depend if you are using or synthetic data or real data. But synthetic data is just for simulation and tweaking on these parameters and for analysis. Large KK, it is very robust to noise, but tends to merge or suppress nearby peaks. So if you have like two blades close each other, again, it causes problem. It will be very well separated without any problem. So next will be MTI filtration on time Doppler map. It is MTI notch filter. The goal will be suppression of zero Doppler clutter. So it is mean I want to suppress static or very slow object, because even movement of trees or jittering of some towers and so on. Even tower is not static object, of course, because always there is some small movement, and this small movement costs you some Doppler shift, but maybe plus minus 1, 2, 3, 4, 5 hertz, something like this. So we consider this that is almost static, and we also want to remove. So for solution of MTI filtration is called a notch filter. In the Doppler time means that is zero Doppler, and we want to remove. We must remove because it is strong reflection that our UKF will always select, or AMPD algorithm always select this value. Yes, it is your one DSC, but it is not true, of course, this DSC, because it is just tower. Sorry. Static clutter occupies a large part of the receiver dynamic range, can mask moving target, especially with low radial velocity. So imagine that you have, okay, some example, UAV that is not moving, just record something what is forbidden, but is in the same position. Of course, there will be rotation of blades, but this is micro Doppler. And what I can say, on the higher distance, the micro Doppler could be masked, because it is not so big reflection of this micro Doppler. It is this periodicity of micro Doppler. You can recognize. If you recognize, okay, you will detect it. If not recognize, it could be almost like static, if you get my point. So idea of MTI filter, or this is design filter with transfer function that has deep notch around 0 Hz. What does it mean? Yeah, I will just remove it. I will just make filtration, okay, for easy imagination in frequency domain. So I will take my spectrum, multiplicate it with this transfer function. If it's around 0 is this notch, then we'll remove it everything around this 0. Now depends how you will set this notch filter, because how I can see this notch can looks like this one, very narrow, or wide one, and so on and so on. So to simplify, to visualization, please run MTI demo application. it is this one. You should see something like this. Workings for everybody? So there is original Doppler spectrum simulated. You can see that there is this free harmonics. It is this is again flash, and this is design of my filter. And there you can see two parameters, width and pole radiation. So it is pole radius, how I am closer to unit circle, and it is width. This is not width parameter that you are setting. So please, this width just define you this place, how far away around zero circle. If you go to, okay, we will play with it. If I will go to like extreme 0, you can see that it's not like this, but there is some width. It is, and if I will continuously increasing, these two lines go to each other and each other and each other. Please be a little patient, because I know that you quickly click, but sometimes take a computation. So it is depend on speed of computer, and if I will go maximum, it will be almost together. Always please watch filtered signal. You can see it is wilder, and if it's wilder, then bigger part around zero frequency is removed. But just be patient. So set maybe 200, something like this. And we will go oppositely, just put to pole radiation, influence. You see now of if I will set pole almost close to unit circle, what this mean? That the zero and poles are really close each other. That will be extremely narrow, and only really small parts will be removed. And now please just tweak this parameter and go down, and you will see that this will be wilder, so I will remove more. And now you need to tweak to your application, because of course if something will be very low speed, then will be your target somewhere around, and it is just controlling mechanism for MTI filter. What you consider that is still static object, and what you consider that is not static object, it is up to you, like radar engineer, something like this. So it is about just designing filter. I show you just principle. So slowly go with this parameter down, and watch always magnitude response, and watch please final static lateral suppression. Okay, check this size will be yeah, higher and higher, wider and wilder. So just play. I will give you 1-2 minutes to play with it. And there you have data source, if you can saw it. And please, after you finish with your setting, just switch to measurement. It is already pre-processed data. I will show you. It is generally like spectrum simulation. It is MAT file, it is just metric with data, it is spectrogram if you open, and this is spectrogram of real measurement. Oh, sorry. Just play it with this and check. I just remove it and just rest of my signal. And now play it again with parameters, please. I will give you 2-3 minutes just what is influence of the both parameters, because there is no description. It is better interactivity on your PC. If you have any question, I will answer you. So if I will go with pole radius to higher values, this will be more and more steep and more close each other, so it will be more and more narrow, and this is controlling of width. So you need to find combination of parameters that you desire, that you want, that you need. There, I can't tell you that exists only one good solution. It is not true. It is filter. It is up to you which filter you want to design, what you want to suppress. But now, after MTI suppression, I can go for UKF. Works for everybody? So about design of notch filter from point of the view parameters, we design it in Z domain, place zeros on unit circle, because we will just it will be deep notch what we want to suppress, and pole slightly inside the unit circle with same angles, so it will be narrow and controllable parameters. There is two parameters, width and pole radiation, and you already play with it what is fine. So output figures we already described, so I think that I can continue. Now we will go to DSC extraction. So prerequisite is that you already have sampled IQ data of radar signal, you already apply MTI filtration, and so you already remove static clutter, because you can't use this one. Always will be one DSC as some other, but we want to detect this free, this, and so on and so on, always in each cut. So in synthetic data will be like this one. So there is extraction of the DSC component. If you will please first run tutorial 04 extraction. It is without guy. and this is result for KK5. Please make zoom on your PC on some part that you want to see, and this small dots, it is extracted DSC component. But how I already told you, it is relatively hard to see in extracted data. And sometimes some values for some KK, you can see it is not fit in good position. Why? Because KK is parameter of where is detection of local maxima. So try tweak this parameter. Just use another value of KK and try different some value that will be bait. It is on a number 48. So plus try 10 and again change and run it and try check what is results. 20, 30, 40. Just continue please with this one. This is for 10, but it is hardly visible. Please run it on your PC because it is better always zoom area and try see which these 3 dots in the same row which is located, and try this parameter for 10, 20, 30 and 40, and maybe you could try then some higher value, but I recommend you up to 40, something like this. I will give you 3 minutes to testing. Just change this KK. It is line 48. But if I will make a lower this image, you can see where is the, how to say, colorful area, where is higher amplitude. So for sure it is always around this value. So but it is hard to, how to see, hard to see this extraction because there is a lot of value. And also check around this flash, there is some problem, there is some extracted value that definitely not fit there due to flash, because he need to choose some value, but it is almost all constant, very intensive value. So try 20, 30, 40 please, and let me know. So if I will put 20, I will get this result, and so on, so on. So please try it up to 40. And one tweaking, check there. There you have parameter mass. It is mean measurement is equal 1, and if you put 0, it will be or simulated data. So try it also on simulation, because there is better visibility due to unpresence of this noise, of course. So you can see that extraction will be always this harmonic DSC. So I will finish this. $40. Yes, and there is nicely visible. Check about this one, that he extracts some 2 values that are each close other, and of course if the sum of all must be 0, then we will just recompute from these two values last one, because it was like f3 Doppler frequency is equal minus f1 plus f2, so he will get results really some high value of Doppler frequency, because results must be always 0, or it is close to cross section, or close to values that are very low, so the last one must be very high or something like this. But now please try tweak it on simulation data. Just put to mass, okay, I will go down again and put mass 0. Okay, check. There is really nicely saw it influence of flash, where this algorithm failed, of course, because we don't know what to select, because it is everything is spectrum is almost very hardly influenced. So he see this value, these two values, because they are highest at flash. But next one to be 0, all three, it is this one. So now please try change, try found me parameter key that will be nicely visible all three sine waves, because already they are this visible, but try to tweak to be better resolution of visualization, better visualization of these three sine waves. Try it, and I will expect what you are told me, which parameter, what will be value of this parameter. So I will try also. There is relatively good visibility. Okay. Always this, of course, this algorithm failed around this flash. Not fail, it is worst result, not fail completely, but
Around 70.
it is very high. I have different value. Okay, let me check 70. 17 or 70? 70. Let me check. Okay, I get your point. It is very nicely visible, but also there is a lot of error. So I am not. I would maybe better agree with about 40, 30, 40. By the way, about it's true that about flashes always is not so accurate, of course. Now you can write, you can run MMTD extraction app, but I must say that this app is relatively, how to say, computational demanding for my PC and sometimes cause problems. So, okay. This, okay, you don't see it, sorry. It is very similar to previous, only it is with GUI, and one thing is that there is, you can make like MTI filtration or enable or disable. So if you are disable, you will see that most of results will be detected when DSC components around this zero frequency. But the meaning of application is same like previous script KK. This color bar, it is just color visualization if you need to tweak, and slice time, it show you just cut in spectra. So please try font time that you just hit the flash, because what will be in spectrum? It will be almost constant. So try to find exact time of one flash. This one, this one, this one, or this one. It is up to you. Just try it. I will also try, so I will remove, just try it alone. Also try enable and disable MTI filter to check how works with MTI and without MTI. And without MTI, a lot of these extracted points will be around zero. So check this. Now I am in time 1.14, and if you will zoom it, it will be close to this flash. And if I will go no,
1.2, around 1.2.
exactly. Now check. Before I am minus 20 dB, something like this, some maximas. If I go 1.2, I am completely up, and my full spectrum is just affected. And half of them, of course, is affected and half is not, because, and if you will go to double, so about this value, so we can zoom, because I don't know what is, it will be 2.2, yeah. It will be just opposite side of spectra. Okay, yes, now exactly. I just jump to up and just cover everything, and imagine that you have target somewhere and now jump during flash and you can't see anything. Try also enable disable this filter. And check. If I will disable filter, there is just white line because always this extraction algorithm told me, yeah, the strongest DSC component is 0, 0, 0, 0. And then select 1 and next just compute. And again 0, 1, compute, 0, 1, compute, and so on. Or something really close to 0, but you can see this one. And this is bad. It will not working because it is not true. It is same like if you will ignore one sine wave. If you will do it like, how to say, 2 blade and tower. And there you can visible formula for computation, this last one. So AMTB select 2 and next recompute. Select 2, compute, select 2, compute. So you always see three points. So if we will go to Kalman filtration, there will be first I will start with some introduction to Kalman filtration. Please first open tutorial 0.04 ukf.m. There will be about script description, what is inside. Input parameters is free Doppler components versus slow time. It is getting from AMPD. It is this free extracted frequencies. Then there is some UKF noise parameters for UKF. First is sigma 1 and sigma 2. It is these 2 parameters I already described. It is process noise and measurement noise. So process noise means how much the Doppler components are allowed to move, in which range of Dopplers. And sigma 2 is measurement noise, how much you trust in extracted bit from MMPD algorithms, how much I trust. It is good confidence, low confidence, and so on. And after you found it, you need to recompute, you will compute this amplitude, make averaging, and then you will find this Doppler frequencies, and then you need to compute all combination, because you don't know that first one was first sine wave or second sine wave, third sine wave, and so on. So you need to make 1, 2, 3, 1, 3, 2, 2, 1, 3, and all these 6 combinations, and make like difference between values like predicted and computed, and the slowest error, it is the best value. So first is extraction of Doppler lines based on AMPD algorithm, then UKF prediction filtration, resolvable label switching with permutation, because I don't know which is first, second one, and for each permutation we will compute the sum of absolute errors for each permutation, and we will take minimum. And this will be correction for UKF. So please open this tutorial. and check output is how your Kalman filter follow this sine wave. And oh sorry, that's again I have on primary screen, not on secondary. So figure 2 is error, figure 1 is look 1 second third sine wave. Why there is always problem? Flash. You don't know it around this, so it is flash problem. Please again you can switch from math from 0 to 1, and then you will load it real data or simulation data. So again please try to also change, you can also change sigma 1 and sigma 2. It is depends if you will believe more in measurement or prediction. So you can tweak this parameter, but carefully tweak please this one. Remember that default value is 100 to 100. With this value works relatively stable. So again take 3-4 minutes and play with this one. For sure try real data, so it is mass is equal 1. If you will just run with real data, you can see what will be result. Just play with it. Try it with real data, try changing sigma 1, sigma 2, and also you can tweak parameter k, what is scale, number of kilogram, it is function, window function. So now we will continue to adaptive filtration with UKF. This is how to say, it is complete tutorial of UKF filtration, stage-by-stage logic of UKF. If you remember from previous lecture, it is just go one by one step from this 12 or 13 step how I have this tutorial. So try it, and there you can see what is output of real data, and this is please like transfer function of your filter, but like one slice is one filter, and of course you are changing this coefficient filter on time based on DSC, and multiplication with your original spectrum, you will get these results. So of course it will fail there because we don't concentrate into flash. But you can see MTI, and the rest also is relatively nicely suppressed. Of course, somewhere could fail. It could happen because it is not mean that work for 100%. It is real data. There could be some additional reflection. There could be higher reflection due to shape of blade, something, and Kalman didn't expect that will be so big changes because he also always make prediction on some behavior. So it is like this, and there you can see every error and average error.
Like we can use also
I will go.
some clustering algorithm instead of UKF. Like for like in ML, we can use curve fitting and all things.
I don't think so, because you need to, you don't have available the whole spectrogram, but you have always one spectrum by time, so you don't know what you to expect, so you need to use algorithm classic filtration. So I don't think so that you can use this clustering methods, because you know you don't have the whole record if you are working in real time, because UKF always works with present time and predict one time and again and again and again, so he don't know future. So with clustration, what do you want to cluster if you have only one spectrum?
Like we can develop a model, like and we can train our model with like pre-recorded data. Then we can.
But you have, I will stop you. You have radar working in real time. What is pre-recorded data? It is previous tracks, okay. So previous track that you have some movement of wind turbines, some kinematics of targets, but what tell you about how will they change in future? Not much. Okay, for 1, 2, 3, 4 prediction, for some slow number of prediction, you could predict if will be big plane. You don't expect that will have this rotation and go back, of course. If will be some UAV, it could be really quick maneuvering, but I think that in this case it will be really hard to design this filter, because it will be must be definitely designed for completely different values, because kinematics, dynamics of this trajectory will be it will be huge. But for sure our filter will stop work completely, because he don't he expecting 3 waves, sine waves, if you get my point. So it will be I don't know, but clustering method like DB scan and all these methods, it is about grouping, how to say, grouping more points, and you, that is one target. I get you. It is like when you have hit your illumination by one, like 3 hits through 3 illumination, and it is not mean that it is 3 target. It is one target hit by 3 hits. Then you use clustering method, but it is just like for that you need to group these 3 hits and interconnect. It is one target. So I don't think that will work for this method. I think that you need to use just really some Kalman filter or some filtration method. I don't think that will work with clustering. It is for another purpose. It is just really that you hit targets more time, more PRIs. And you need to tell him, okay, all this group of hit, it is one target. But imagine if you have 2 targets close to each other, and you get like point of like hits like 10 and 10, and it will be 10 and 10 points close each other. It will be really close. It will be really hard to separate, and maybe your clustering method failed and told you it is one big plane, not too small. But it is something else. It is clustering method is something else. It is using in, of course, in radars. We don't talk it during second lesson about it, but this is use it very much. You need, because always imagine some really big ship, 400 meter ship or something like this. You know how many hits you will have, and you need to make clusterization. And it is now depends 2D clusterization, 3D, it will be cloud of points, and so on and so on. But no, for this you need to use filtration method. Okay, please open tutorial for not UKF but filter. Okay, there. Run it. And you will get transfer function and suppress it. So you can see how nicely suppress all this DSC component for some setting, and this is transfer function changing on time. And now we are going for complete algorithm. So please open, okay, where is my mouse? Open after you finish work with filter, open folder complete, and there you will see Kámen, Protivanov, Austria 1, Austria 2. So open Kámen and K01, and open please this K01 prediction DFF and this one with date. So tutorial complete Kámen K01. And it is only measurement. Also, please check the whole algorithm, because there is just whole algorithm. You can recognize easily individual equation where we compute time delay, distance, range, and so on. Just please pass through the whole script first before you run, because you can easily change individual part that I mathematically described yesterday. It is just completely like equation that I show you. So just go one by one, please. Didn't work?
P01. Which file?
No. Just tutorial 4. Go tutorial 4. Yeah. Complete. Kámen. Yes.
P6.
Yeah. 2. Sorry. I missed K01, not K06. I think there you have. Sorry. It is just another data, so there is no problem. K06. And this second one, by the way, first one and second one, they are same results, only without it is just graphic visualization. I make correction for smaller screen. So we can pass through the whole algorithm on this. It takes little time.
9 figures. 9 figures.
No, it is nice 9 figure, but unfortunately on my primary screen. So give me a second. You will run later another scenarios that is from individual measurement. Okay, you should see something like this.
Yes, sir.
Original spectrogram from Kamen locality where we made first measurement. Yesterday you made analysis where you can find best place where we can measure. So we get this measurement. First we design MTI filter with some parameters. MTI filtration, static, tower is disappear. We extract in individual cuts 3DSC, there you have detail, sometimes fail, sometimes not, of course, close to flash fail. This is average error, so about 45 Hz. This is predicted and extracted value. Sorry, this is what we what we select, which DSC. This is transfer function of our filter. This is after filtration. And now, please, you can run K0, 1, 2, 3, 4, 5. But on your screen, because always all visualization will be on primary screen, so I need always just changing. But always you can see 9 figures. It is one by one, one by one. These data are already pre-processed, so it works always with all this MAT file, all this measurement, everything. It is just about changing of name of this MAT file, but it is individual measurement, and it is for locality Kamen, locality Protivanov, locality Austria 1 and Austria 2. So just check that everything working. Please run one by one, special, maybe one scenario per one geographic place. Just check it that algorithm really works with different distances, different PRI, setting parameters. And I didn't mention all these parameters because you already have in tutorial 3 this length of pulse and all these things. It is just repetition, it is not necessary. So please just play it, try open also Protivanov, try also Austria and Austria 2. I give you 5-7 minutes. If you have any question to any result, just let me know. And then we go for conclusion, because this is total, this is complete output, like visualization of individual step. Honestly, we usually present only first and after filtration. I don't need this individual step, of course. But if you want to check how design another type of filter or with another parameters and so on, so you can easily adopt it and check individual results. I think that there is all. Of course, there is some zoom and so on, but it is just for you, for more detail to present you. But we generally. So try open now Protivanov, if works for you, this result. This is Protivanov. Okay, see again around flashes.
Flashes.
Yeah. Transfer function, yeah. Then try Austria.
No, I did in Austria. Now I'm going to Protivanov.
Oh, okay. Yeah. Try Protivanov. It is little demanding. Of course, there is a lot of computation, so it depends on your PC. Yeah. Again, and when you open Austria, there will be this aliasing thing, because due to size of the blade, there was bigger blade speed, and it is start aliasing. So it was a reflection of this flash on other side. So just try open it.
I think we don't have Austria 2 file.
Yeah, maybe you have only Austria 1. Yeah. If you want, I can later upload also. So just. Okay, so that is some. Until it's warning, it is okay. Yes. Like this, exactly. It is flashes, and there also it is. Yeah, it is. Only small part of flashes, always like reflection to other sides. So I hope that was enough proof from several sides that workings. Of course, it could maybe require for some really strong reflection or some bigger turbine, some tweaking of parameters of filter or something like that. It's possible, or tweaking of MTI filter or something like this. Of course it is, but it is not so hard. You have complete simulator model, so you just change one function and you could easily adopt it. But the general principle working. This is me. But you already saw it, you play with it now. I just want to show you locality Kamen, Protivanov, and okay, Grobschweinbach. I probably have a little different data. There you can see very nicely these flash reflections. Even after removing original, after suppression, still this remains, because it is this flash. Continue, we are outside, so we need to map to inside, and aliasing occurs, and it is still back and back. So it was last slide of tutorial 4, and now I will continue with the last lecture, if never mind, or can we continue? I will just ask. Time management is important. So we will look now to the whole story. We start Monday morning at 10 a.m. until 4 or 4:30 Friday p.m. 22 hours we spent each together. No, I'm joking. So there is just course review that we start. What is primary radar? What is range, Doppler, filtering, ambiguities. Then we description of wind turbines, radial crater, microdoppler. What is this phenomena? It was important part because we need to analyze. If we want to suppress something, you need to understand what do you want to suppress. Then we define mathematical description of behavior simulator, and of course we need to make validation of the simulator. So we designed, you already know how design measurement chain, what you require in principle. I told you that is in principle. I show you own solution because we have this equipment. If you have another equipment, it will be tweaking of some parameters, some setting of difference, carrier frequency, bandwidth, sampling rates, and so on. But now you understand why you need to choose these values due to connection, interconnection with radar parameters, because you need always measure something what is similar measurement in radar, and very often you can just borrow somewhere some radar and go to measurement. Also, I told you why it's important that we can go just take equipment and go measure. It is very dangerous. We need permission. So it was this one, and then we continue. Then I want to highlight how important before any measurement is analysis, like geoanalysis through map, through digital elevation model, and through line of sight. That you can't use just only 2D map or something like this, but always check real terrain, and one of the best tool, OpenStreetMap, how you could even through this overpass website, how you could extract only object that you are interested, and how it's very important and save a lot of time, how to say, this panorama or street view before you go to this location. And especially in your country, you are a big country. In our case, it is still few hours. In your case, it could be a lot of hours, of course. So this is important. If you remember this Anenská Studanka site, there was almost impossible found even place for measurement because everywhere was woods, it was in mountains. If we was enough in adequate distance, there was some valleys and was some hills, something like this. So sometimes it is not easy to find even place where you could measure. And we end with lecture 7 and tutorial 4 that was today, and it was just related to our mitigation techniques, where main contributor was my colleague Karel Jurica. I need to mention them because I really thank you that I can cooperate with him on this. And lecture 8, it will be just conclusion, some limitation, what is open problem, what we can improve, and future work. So if before our future, what we can do it, where could be improvement, you already know that wind turbines behave as strong time varying, and it is the worst, moving clutter for primary radars. Close to airport could be disaster. Echoes is very variable, RCS, radar cross section. Why Doppler spread? It is depends of course on speed of wind turbine and length of blades, if I could simplify it, and of course shape of blade. And this behavior has a strong masking effect So weak targets could be masked or just disappear from your radar, and it could be very dangerous situation in case that will be, like, imagine that you have some small aircraft around wind farm and now you are lost both of them and you can't control where are they, so it could be dangerous. This also depends, we also make exploration inside what is inside radar signal processing, not from point of view hardware but more in software and block processing chain. So now you know why we select each frequency band, PRIs, pulse width, beam width, what is range Doppler resolution, and so on, how we can make visualization of outputs on radar. It was this A scope, B scope, C scope, and PPI from different point of view, and so on. So I hope that if you don't know with this information, it will help you now little understand what is inside radar, that usually when you go to close airport, you see not exactly radar, but you see only antenna of radar, if I can say, but there is much more things. So I hope that maybe you will start liking this area and will start working in this area. There is a lot of different opportunities also for job, antenna design, amplifier who likes analog techniques, power amplifiers, AD conversion who like only software design, algorithm design, signal processing, tracking algorithm. Now in present system and in future system, for sure you don't want to know only there is target, there is kinematics, there is his kinematics, there is this position. You also know what is type of target. It is helicopter, it is some small, it is ship, it is small plane, and even it is still improving, and future will be that based on RCS signature, I think that in soon future we even can recognize. So like example for UAV, you will detect UAV, you know where it's going, you know kinematics, everything, and later you will see from behavior, okay, microdoppler, it is 4 blades, so it is quadrocopter, and from behavior of quadrocopter maybe you will recognize, okay, it is Maverick 4 or something individual type. It is open future. But of course, a lot of methods of this signals processing is extremely numerically demanding, but we have still more and more powerful computers, GPU computing and all these things. So algorithm that was not possible use, even that are known before 10 years, we can use now, and who will see what will be after 10 years, where will be. Also, there is important that in present time start be very interesting fusion of information from different sources. Imagine that your radar also have access to some precise GPS or ADS-B, so it is mean that in same time when he measuring reflection and all these things that I mentioned, he also receiving information from secondary like ADS-B recorder, so he know, okay, there is some plane, it is this Airbus 77, I don't know. So you could make fusion from different sources. You could use also information, public information from OpenStreetMap or military maps about position of wind turbines, and so on and so on. So it is not only about radar, it is about fusion information from different, totally different domain. And if you, and you know it, if you have more information, you are clever, you are better picture. And it is always like, So, what we achieve, we make the whole wind turbine eco-modeling, we design model, and then we design mitigation algorithm. I can say that I hope that I also introduce how make this measurement campaigns, how important is metadata. I will again highlight that is extremely important, and what do you need. Then last one was mitigation concept. I will not repeat it because we just finished it, it's clear. And now I would like to highlight what is future work, and it will be probably very demanding. Maybe you have some more idea what could be improved, because we just think about few things. I think that very interesting looks multi-sensor cooperation. Why? Imagine that you have multiple sensors in different position. Wind turbine is static object, of course, in one place after installation, only blade is rotating. So in case that I can't see targets from my radar, but maybe could be visible from another radar. If I have multi-sensor fusion, okay, you lost information due to position of blade, but if for my radar is bad position, strong reflection, everything goes wrong, it is mean that from other side could not be so bad. So multi-fusion, I think that is also future of radars, but it is not easy, because you know that radar works in local coordinate system. If for one radar is target like 1 kilometer far away, for second radar could be 10 kilometer. It will be second target, and for first one will be 5 kilometer. For second one could be kilometer. How you want make decision, how you interconnect this multi-fusion information, how you can be sure that how you can want interconnect this to correspond to one target. And 1-2 target, okay. In the worst case, you will try all combination and one will be best. For 20, 40, 50 targets, forget. A number, imagine if you have like 3 radars, 50 targets, number of combination will be 3 to 50. It's a lot of combination, and only 50 of them will be correct. The rest is lie. So this fusion information is also not easy task. Application of cognitive principle, we just discussed it with your colleague about cognitive radars. So it is a perfect example. It could be include utilization of meteorological and wind turbine control data. So do we have some site where is information about wind turbine parameters, that wind turbine now rotating speed is 7 RPM? Can I use it like another source of information? If yes, it will be perfect, because then if I know this base parameter or rotating yaw angle, then I can predict that this is reflection from this specific wind turbine, because I can model it, and so on and so on. So different domain of source of information is important to make fusion and fusion. But imagine, it is relatively easy to say, but everything needs works in a real time. You don't have so much time think about these different sources, how combined. It is completely different format of data, and still you need to work in real time. If computation will take 3 minutes, it is nice. But after 3 minutes in standard plane, you will be far, far away, and it is outdated information. So this is second thing. Then adaptive configuration of signal and data processing. It is now a huge task, and I think that will be close future. What is mean? Example that I have target that is hardly visible for some setting. Okay, I need some logic in my sensor that, okay, there we probably is target, but is hardly visible. I don't know what is this. So he will automatically change length of pulse, intermodulation, some all from thousands of parameters, and automatically set and measure again, but automatically. But please don't consider that is automatic like machine learning on AI. No, this must be controlled logic. So maybe in some late future will works like this, but I would like say optimization of radar resources. It is better. Don't expect like it's really popular now that is everything is AI or something. No, no, no. You don't have control, and you need to have 100% control on radars. It must be predictable device, how operate in which scenario. And of course, future work, it will be nice if we will have possibility implement this some mitigation technique and some these things to real radar sensor to signal processor and validate that really works on a real radar. And it is depends, of course, on which type of radar, and it is depends on. This is tightened with industry cooperation, of course. Okay, after finishing ceremony, I definitely will ask your feedback on course, so then you can hit me if you like it or not, or give me suggestion, or what should I make more extension, what should I suppress, and so on, because of course we are, me, Karel, we doing our best thing, but just we are 2-3 people who working on this course, so we need more opinion. So please, if you don't want say me personally, or you don't know now, later you have my email in every slide, at the end slide, so just send me email, because there is always space and for improvement. So I really want to thank you for participation on this course. I really appreciate it. I think that we have good time during even lunch or tea break or coffee breaks. I think that we discussed a lot of things, not only from this area, but even from personal area. So it was really refreshing. It is always nice met new people, and I hope that through your especially mentors that I know very well, we will be in touch. So thank you very much, and it was last slide from my side. Thank you very much. So probably now we'll take some. Sorry?
Pictures. They want
Yeah, true. Maybe we could ask somebody if any, yeah.
can
Had some professional photographers.
मेरा मोबाइल से भी ले सकते हैं। तो मैं ग्रुप में भेजूँ। एक सेकंड। ऐसे क्लोजिंग सेरेमनी भी है, पर अभी हम लोग फ्री हैं तभी भी स्वीट कर रहे हैं।
ये वाला कैमरा चला
पता नहीं सर आ रहे हैं।
ये वाला कैमरा
अभी एक क्लियर दिखता है।
एक स्टूडेंट के साथ ले लीजिए सर
ये वाला कैमरा चला
So I will just run something like this and not see my desktop screen. So we will go there. Yeah, it will be nice. Please come, all of you.
And actually one more, my colleague is not here, that's why I'm calling.
We have time, so no worries. Come.
ऐसे ही रहना
ठीक है ठीक है
मेरे मोबाइल पे ले लेना
What?
कोई नहीं मैं उठा लूंगा
Okay, I also will ask. Sorry, my phone. You can also.
कैमरा मैन का फोन है बहुत एक्सपेंसिव कैमरा लगा है
हेलो सर अंदर आ जाइए हाँ हाँ फोटो क्लिक हो रहा है अरे
Okay, and
आप
please,
2 मिनट रुक
my-
सकते
my-
हैं क्या आप 2 मिनट रुक सकते हैं क्या वो आ रहे हैं इसलिए
It is true. Please, yeah. For sure.
ऑर्गेनाइजर ही नहीं थे नहीं
Yeah. Come.
कैमरा से तो ले लेंगे बट मेरे फोन में भी ठीक ही आता है
Okay, thank you.
completed the entire this lecture completed na
Yes.
okay
Yes.
they will be coming by 3:45 or 3:50
Never mind. It is just 15 minutes, so
sir
अभी क्लोजिंग सेरेमनी
because
so you want water